Today we have a probability problem that deals with counting multiples of 72 in this particular case. I want to show you the floor function way of counting multiples. It's what most of you just do in your head, but let's say you want to know the number of multiples of 5 less than 38. We're going to write down the floor function of that quotient. Yeah, and the floor function is just the greatest integer less than the input argument. All right. So in this particular case, that particular number would be 7, right? 38 divided by 5 is a number between 7 and 8. So you actually return this number 7, which is the greatest integer less than the input argument. Now, to convince yourself this is indeed the number of multiples of 5 less than 38, we can just enumerate them. 5 would be the first one, 10, 15, 20, 25, 30, and 35. And again, the floor function is just kind of a formal way to do this. This will be done in your head, really, you know. But this is the formal symbol that counts that number of multiples. Do we have 7 of them here? 1, 2, 3, 4, 5, 6, 7, right? Okay. Now we're supposed to find the probability that a randomly selected 4-digit positive integer is a multiple of 72. Now, you know, random has kind of a controversial definition. It just means that any number has an equal likelihood of being selected. Okay. So now every probability question at its core is the number of desirables in the numerator. The number of desirables here is the multiples of 72, and then divided by the total number of possible outcomes. Okay, so we can write that down very easily here. This would be all the multiples of 72 between 1 and 9,999. But let's take a look at this denominator term first, the 9,000. Where do we actually get that? Well, we're talking about multiples of, we're talking about 4-digit numbers, right? So 1,000 is the smallest 4-digit number. 1,000 is the smallest 4-digit number. If you subtract 1 from 1,000, you get 999. That's a 3-digit number. All right. So we're looking at all the numbers in the range 1,000 to what are we looking at here? We're in the range 1,000 to 9,999. Right? 9,999 is the largest 4-digit number. Okay. Well, there are 900 of these. And again, this is the standard. It's 9,000, excuse me. This is confusing to a lot of people. One way to avoid the confusion here is just think if you have the numbers 1 through 2, that's 2 numbers. 2 minus 1 is 1, so you have to add 1, right? So you have 9,999 minus 1,000, which is 8,999 plus 1 is 9,000. Okay, so there's 9,000 positive 4-digit numbers. Okay. That's the total number of desirables, if you want to call it that. Now, the calculations here, this number is, I'll just go ahead and write it directly above it to save some writing. This number is 138. You guys can verify that. I double-checked it, pretty sure I got it right. That's 138. And that would say there's 138 multiples of 72 4-digit numbers, or numbers less than 9,999, which would include 1 through 999, right? But we have to subtract off the ones less than 1,000, so that's what this is about. So this would be, we have minus 13 here. And so y'all, what I ended up with is 125 over 9,000. But now this is a fairly easy computation if you don't feel like using your calculator. Notice this is the very same thing as 5 cubed in the numerator. 5 times 5 times 5 is 125. So we have 5 cubed And this bottom part is just going to be 9 times, now 10 is 2 times 5, and that would be cubed also. So you would have 2 times 5 quantity cubed, right? Okay, but notice here that you got a pair of 5 cubes. You have a 5 cubed up here and a 5 cubed down here. So this is actually just equal to, the 5 cubes cancel, and so you have 9 times 2 cubed, which is 8, which is 9 times 8, which is 72. Oh no. Okay, that's equal to 72. And sorry, it's 1 over all of that, right? Can I write it up here? Will it go away on me? Okay, so it's 1. Y'all, looks like my marker went away, but the answer here should be, let me get the marker working again. The answer should be 1 over 72. Okay, y'all, I couldn't get the 1 to appear right up here. Yeah, 1 over 9 times 8, and then that's 1 over 72, right? So that's the final answer, which is kind of interesting, isn't it? Because it was multiples of 72 we were interested in. It turns out this is a special case of a SMO junior problem, I think, or maybe an SMO senior problem presented by Wei Tan. And he did it for like 288, but this is just kind of a fluke of nature, I think. But anyway, it's kind of intriguing that the probability turns out to be the reciprocal of the multiples we were interested in. Okay, so that's 1 over 72. Let me know if you caught a mistake, but I think I got it right. Okay, all right, that's all. Thanks for viewing.